So how well can a large language model like GPT-4 solve problems just by using the world knowledge it's been trained with? A year ago today, Google released a paper that was all about using a large language model to generate Python to control a robot. Now that's when I first realized how powerful large language models can be, and they just weren't used for creating Shakespeare in a pirate style, for example. They could be used to control and solve problems in a very sophisticated manner. The problem with using Python, though, is that it's quite rigid. It can't adapt to evolving situations, and it's very hard to build in any error handling. So could we build something that's a bit more flexible to solve problems? To see how well a large language model like GPT-4 can be used to solve action-based problems, I knocked up this very simple RPG. The task will be to put some wood on a smouldering fire. There are a series of simple actions that can be called to control the agent. The simulation also enforces world logic. You have to be close to something to be able to pick it up, and you have to be holding something to be able to use it. This RPG can be controlled through very simple text commands, such as moving to an object in the world, picking it up, putting it down, using a held object on another object in the world, getting the status of objects inside the world and what the agent is holding, and also quit, allowing us to say when the simulation is finished. We'll give GPT-4 a prompt of put some wood on the fire, and also give it the initial status of the world. So in the background, this is how it's all working. Our initial Python script calls GPT-4, and with the initial prompt and the world status, GPT-4 will then return a command to call. We then pass that command onto the simulation, which is written in Godot, a game engine. We then execute the command or return an error. That goes back to the Python code, which we then give to the large language model, GPT-4, to execute. It will then give us the next command, and this process continues until the large language model tells us to quit when it thinks it solved the problem. So let's run the agent code and see if GPT-4 can get the wood on the fire. And it looks like that failed. Okay, GPT-4 is telling us to run two commands at the same time. Now that's normally fine, but in this simulation, which runs like clockwork, it can only handle one command at a time. So let's put in a bit of a hack to basically ignore any other command than the first one. Okay, hack implemented, let's run that again. It works. The tree was cut, the resultant log was put on the campfire, and now it's burning. And at the end, GPT-4 called the quit command. It thinks it solved the problem. Let's run that a few more times and see how robust this solution is. Now, after a total of 10 runs, we can see that the lowest number of commands is 9 with 2 errors. The best way you can solve this problem is in 7 commands. So that's not bad. And if we look, the type of errors that we're seeing are things where the agent doesn't yet know about the world logic. It doesn't know to have to move towards something to pick it up. But why is there so much variance? Well, this is down to the temperature of the network. Temperature is a measure of how creative and diverse the output of the large language model will be. Now, we're using the initial setting, so it's going to give a range of different answers every single time. If we increase the temperature too much, then it might get more creative, but the commands that it gives might be completely uninterpretable by our simulation. So we want to keep it at its current setting. Anyway, the end result is this all works. Let's try a different technique. Let's try a technique called chain of thought. We're going to ask the large language model to output its list of commands first before it starts executing them. Let's change the initial prompt to give us its plan first, then to give us its first command. And here's an example of the initial prompt returned by GPT-4. Running again for 10 times. and the results are worse. So the problem is that the plan is written from a point of naivety. And once the plan is output, the large language model is much more likely to follow the bad plan than it is to react to the situation in the world. So let's try a different technique, prompt rewriting. This is where we ask the large language model to come up with a better initial prompt based on knowledge that it's learned from the previous run. This might include things like you must move towards an object before you pick it up. So any knowledge and errors that it discovered in the first run will then go and help improve subsequent runs. So here's an example of a new improved prompt. It's a mixture of tips and a plan. One of the tips, for example, is to move towards an X before trying to pick it up. So after 10 more runs of prompt rewriting, let's see what the results are compared to the original reactive method and chain of thought. It's much better than any of the methods so far. Well, of course it is, because it's using all of the knowledge of all the errors and world logic from one run in future runs. For completeness, let's check prompt rewriting mixed with chain of thought together and see how that compares to all of the other methods. Yep, and it looks like it's an average of the results from prompt rewriting and chain of thought, so not really a surprise there. The best technique is still prompt rewriting, but overall, if we don't want to have an initial run where we pick up all of the world knowledge, our original reactive method is still just as good. So what have we learned? A large language model like GPT-4 can be used to solve action-based problems just using the world knowledge that it's been trained with. As long as the simulation that it executes in can give it feedback on all of the errors and give a hint of the environment and the status of the world, the large language model can correct for any errors along the way. This technique won't work for things like creating a surgery robot where you can't make mistakes as you go. It'd be interesting to see how this scales to much more complicated problems where there are multiple solutions to a problem, or where there are multiple steps in order to come to an outcome. That's it. Thanks a lot for tuning in. The code's on GitHub on IPutABrainInIt, and if you learned something from this or found it interesting, throw me a like, and I'll see you in the next video.